corrections in today? What is the only thing that you have for spring break? Section 10.4, and that's it. Section, no, not 10.4, section 10, what are we in, 6? Yeah, section 10.6, and that's it. Let's go ahead and, there we go. Get to our graphing calculator. So you guys were supposed to go ahead and put in t squared minus 4, and then t over 2. Kiddos, do these equations look the same or different? They look different, but what ended up being the same? We're supposed to be filling in this blank. What ended up being the same?
It's the same graph.
Yeah.
But not the same time.
What did we call it, though? We didn't call it a graph in our notes. Go back and find the technical term for what is the same. Plane curve, or another way of saying it is the same path. The same plane curve or the same path. They're on the same path, but guys, just because you're on the same path as something or someone, does that mean you're necessarily with them the whole time? And the answer is no. You could be driving on the same road, but be at two totally separate places and be going two totally separate or different speeds, right? So when you graphed it in simultaneous, let me make sure I'm in Zoom standard. That should be good. What did you guys notice? Did they go on the same path? And the answer is yes. Did they go at the same speed? And the answer is no. So same path, different. I'm going to put it this way now. Hold on. I didn't cut it down. Did you guys cut down the t's? Could we have cut down the t's? Yeah, we could have graphed like from -2 to 3, but since we graphed them at the same time, I didn't go ahead and change that because it would have been hard to change for one and not the other, etc. So I didn't change the t's. However, I think if you do -2 to 3, the problem is this guy comes from behind and is on a totally different path. But if you start at 0, you can see it a little bit better, and that's what we did. So, how would you answer this again? Oh, God, I'm sorry. There was a million things in my head. Come back to me a little bit.
Okay, thank you.
Luca, you're the only one that doesn't get one. Everyone else?
Huh?
Oh, because you're bound.
No, it's vote.
People in the back, would you vote for everyone that said something today?
Thank you.
Luca, you have to fill out 3. The 3 people in the back that they said wait for circle.
Vice President.
You guys.
I'm definitely going
Write your name under all of them. Alright, as soon as you're done, pass them up. It's a formality, and like there are certain formalities. Showing your votes to everybody.
That's like.
Everyone must vote.
Oh!
Everyone must vote.
I'm a good person. That might be a little illegal, but that's okay. Because you're going to stop here.
Yeah.
Alright, kiddos. Same path, different times. Same path, different times, which indicates same path, different speeds. Anything else unique that can happen in parametric? In functions, how many graphs are there for y equals x squared? How many functions can be that path in function mode? 1. Y equals x squared. Well, I mean, I guess you could do y equals 4x squared over 4. So what is it really? X squared. But in parametric, do these look the same? No. They don't look the same. And yet we'll see in something today called eliminating the parameter, we can actually see what they are as a path, not including the time. Because even though the parametric equations look different, they are the same path. They're just going on the same path. Or they're traveling the same path. Different times they're in different positions. So, let's come back here. In order to help us figure out how can we tell mathematically without a graphing calculator and without making two huge tables that these are on the same path, just going different speeds, and this is the answer. Eliminating the parameter. This is the answer. Eliminating the parameter, which is the process of finding the rectangular equation. Let me help you out with what that means. The rectangular equation, aka the function mode equation. That's just how our calculator says it though. The y equals f of x, no t's. Process of finding the rectangular equation that has the same path. Now the rectangular equation doesn't have the time, so it won't be the exact same thing. But the path will be the same, just the time will have been eliminated. So we don't care about the when, we only care about the where. Because your brains don't think parametrically in the sense of how to graph. You guys think rectangularly in the sense of y equals x squared is a parabola, y equals mx plus b is a line, y equals square root of x is a square root function or a radical function. Y equals 1 over x is a rational function and has an asymptotic. You guys think rectangularly, it's how we've trained you to think about graphs and paths. So when these parametric guys come along, you're like, what's that look like? I don't know, there are t's. Maybe it's a parabola at number 11. Maybe it's a line. How can we know for sure? If you are a highlighting kind of person, if I were you, I'd go ahead and get a highlighter and I would say to eliminate the parameter. Solve for t and x, plug it into y. Solve for t and x, plug it into y. That's the process, that's the idea. There's only one rare time with, it's actually not rare, one time with trig. If there were trig, we'd have to kind of go a different route. It gets trickier with the trig. But if there's no trig, all we gotta do is solve for t in the x equation, plug into the y equation, because we want a y equation in the end. Can you guys take me literally at those two steps? How would you start number 11 if that's literally all you need to do?
Just multiply by 4 on the x and then plug it in.
Take the x equation, multiply both sides by 4. You're trying to isolate t to t alone. So then we can say that implies t is equal to 4x. Where are we going to plug that in? Y. To the y equation, right? So we can go ahead and take the y equation and say, okay, y is equal to 4x quantity squared. Does this look more like something we should recognize? Yeah. So even though these are, or I should say, this is a pair of parametric functions, the path that this particle or this object is moving on in these parametric functions can be seen by y equals 16x squared. So why is that helpful? Well, some of you would have seen the squared and assumed it was a parabola. That wouldn't be necessarily bad. Sometimes you'll be right, but sometimes you'll be wrong. Just because there's a square doesn't always mean it's going to be a parabola. But if we eliminate the parameter and see the parabola, then we know that's the path. We can even kind of say that path because we can say this parabola is going to have a vertex at 0, 0. Because it hasn't been vertically or horizontally shifted at all. When x is 1, y is going to be 16. When x is negative 1, y is going to be 16. It's going to be a very narrow parabola. A question, can I show which way the motion is moving? Just with this? No. Can I tell if an object is moving to the left or to the right? No. Can I tell exactly where it is when time is 0 or time is 1 or 2 units have passed or 3 or 4? No, I have no idea where it is on this path. But eliminating the parameter lets me see the path. Does that make sense? What we would call the plane curve. So it puts it basically in terms that we kind of understand better. But the purpose of parameter, again, is not only the where, but also the when. Let's keep on playing with this, how to picture the path, how to put it in terms that we understand better. What if I was to give you another example? Another example. Except in this example, it doesn't just say eliminate the parameter, it also says adjust the domain, meaning the original parametric equations have a limited domain, which would need to translate to the rectangular equations as well. But we'll talk about domain in a second. For right now, just try to eliminate the parameter step. Solve for t in the x equation. Plug into the y equation and simplify. As much as possible. Thanks, Kayla. A little bit more algebra on this one, huh? They're not too bad. Still enough to keep you a little busy. Taking notes on my iPad so I can save it easy. Alright, cool kids. So when you solve for t, hopefully you do this one. What did you guys do to solve for t? Square both sides?
I think we have to switch both sides.
I would have probably multiplied and then divided. That's what I would have naturally done, just to try to get that t in his own place. But you could square both sides right away, it is valid. Once you square both sides, now what?
Switch.
Switch? Some of you got a little stuck how to get to him. Remember, we have to undo the division. Right now it's trapping the entire expression. So we need to multiply it to the other side. When we do multiply it to the other side, we can divide by x squared. We multiply up t plus 1 and we divide x squared. They just switch places. Now is it a bit more practical? Or a bit more possible? Solve for t. Is that right? Sure. What do we do with that t? Hold on, double check me real fast. You guys agree?
Yeah.
Okay. We're going to plug it into the y equation, right? So you plug in for t, so we end up with y is equal to 1 over x squared minus 1. all over. If you guys tend to confuse whether or not the minus 1 is in the denominator, maybe don't draw the slightly fractions like I do. Maybe this would be a bit more obvious that they're separate. Then I can plug in 1 over x squared minus 1 plus 1. Oh, well, that's nice. It's minus 1 plus 1. Remembers the Uganda now. How do I simplify this? What's the trick?
I bring the x
I
up,
I
put
separated
parentheses.
them.
I put
That's fine.
parentheses
Did you
on
really?
the top and put x
You
squared.
did this over this minus this over that?
Yes.
Huh.
I put a parentheses on the
Works.
top.
I just wouldn't have thought of it. What'd you do on top?
Parentheses on the top, bring the x squared up.
That's what I would have done. Guys, all of these are proper variations. I like getting rid by multiplying by the reciprocal on the bottom and on the top. And not just the reciprocal, I just say the denominator. Makes everything simple. But you could multiply by the reciprocal, just make sure you distribute it to both terms, which is what Sean did in splitting them up and dividing both of them by 1 over x squared. So all the variations are proper. You could have even gotten a common denominator and then multiplied by the reciprocal. I just like this one because this one ends up saying, hey, those two cancel, sweet. This one distributes. What's x squared over x squared? 1. And what's x squared times 1? So what's my path? What's my plane curve? This guy. Except, they don't just ask for the function, what else do they ask for? The domain. If you guys look at this parabola, is there anything that would cut down or cause this parabola in and of itself, just here, to have a restricted domain? Any denominators? No. Square roots? Logs? No. Straight like tangent that had vertical asymptotes? No. What's its natural domain? All the numbers. Then why is it restricted? Where did it come from? These ones. And is there anything natural that would restrict those ones? The answer is yes. Can we figure out from the original parametric functions, what is t not allowed to do or be? Can't be negative. Negative what? Can't be negative 1. Because that would make a denominator equal to 0. So it can't be negative 1, but what else can't it be? Let's check it. 0 plus 1 is good. 0 plus 1 is good. Oh, no, 0 is okay. How about negative 2? Negative 2 plus 1 is negative 1, that's fine. Negative 2 plus 1 is square roots.
Has to be a natural number.
Yeah. T can't be negative 1, and t cannot be less than negative 1. So how would I say that in a positive way? It can't be negative 1, it can't be negative or lower than.
Just must be greater than 1 or
Yeah, that's the positive way of saying it. Not what it can't do. It can't equal negative 1, it can't be less than negative 1. Say what it can do. Okay, it can be greater than, negative 1. Well, how does that help me with domain? Oh, just go write t. What's the domain in that function? X's or t's in your final boxed equation? X's. Well, stink. How do I know what x is allowed to be? We have two options. Number one, we could start graphing this puppy and start at negative 1. It's not going to work. Go to negative 2, negative 3, negative 4, and look at it and see. Or, who's the only guy we really care about? Domain is what values? X's or Y's naturally? X's. So for our rectangular function, y equals our function with x's. We just care about the x's. So can't we go and take a second and say, all right, hold on. What's going on with the x's? And if we say that t has to be greater than negative 1, x of t, what's going to happen if I was to put a little greater than negative 1 in there? Now that's awkward because it's like, why don't I put in negative 2? I could. What would happen if I put in negative 2? Oh, that's imaginary. What if I put in 0? 0 is greater than negative 1. What would I get? Zero plus 1 is 1. 1 over 1 is 1. Okay. What if I put in 2? Yeah, that's gross. 1 over root 3. Okay. What if I put in 3? 1 half. These getting bigger or smaller? What if I put in like 8? 1/3? If I put in 8 is 1/3. What's going on with my x's, guys?
Decreasing.
They're decreasing 1 half, 1/3, eventually 1/4, 1/5. Okay, well what's going on if I go the other way? Is there any way I can get closer to negative 1 from 0?
Negative half.
Negative a half. Okay, so what happens if, let me make it easier. What if I put in negative 3/4? If I put in negative 3/4, what's going to happen? It'd be 1/4 square rooted, which would be 1 half. What happens to the 1 half? It becomes a 2. Crazy thing is, what if I went ahead and put in negative 8/9? That'd be 1/9. That'd be 1/3. Flip it. That'd be 3. What if I put in negative 15/16? That'd be 1/16, which will end up being 4. Wait a minute. So x's grow the other direction? So x's shrink this direction. X's grow the other direction. Okay, what's the one thing x can't be? Is it possible to have x equal 0? This has to be a non-zero, because 0 is not going to work. So there's no way to get 1 divided by something to ever be 0. Is there anything else that can't come out of the square root with a 1 on top? Negative numbers. So x can't be 0 and x can't be negative, but besides that, kiddos, x can be anything, everything else. Now, some of you are like, I don't like what you just did there. I hear you. I hear you. T can be negative. Struggle, right? With parametric, it's a struggle because we have an independent up here with t's, but then we have x's that end up being an independent down here. If you were to graph this function in your graphing calculator, there's another way of visualizing it. In that we could just go ahead and clear out those old ones that we put in just a second ago. Let's clear out him, let's clear out him. One more. We could use our cool nifty fraction you do. We could do 1 over square root of t plus 1. Remember, kiddos, the question that we ask when we're looking at a graph for domain? Is it how high, how low, or how left, how right? How left, how right, because x is a horizontal measure, right? Right, left measure. Not sure what that is. Okay. That was the graph. Let's see. Do you guys see how left going anything beyond 0? How right? Well, you can go right forever. It's just going to keep on going and going. But how left? It's not going to go negative, hence we can no greater than 0. And if we try to plug in, which I don't know how we try to plug in this mode, if we tried to see if x could be 0, there's no way 0 will ever come out. Okay. It's a bit of a struggle with domain in the sense of you have to know the nature of the graph. So a table might help in that you kind of see the picture of what's going on. But you might have to do a lot of points in order to figure it out, which is what we had to do on this one. So we think about the domain restrictions of the beginning of t's and how that translates to the domain restrictions of x's in rectangular. That's your final answer. Now what if, okay, good thing is this doesn't say anything about domain, right? Whew, no domain. What if we were given something like this, kiddos?
solve for theta?
We have until 59. People in the back, you have about 10 minutes. There's no T's! What's going on? Parametric equations can show up two ways. One way is with time, and our calculator uses time. But another way is with thetas. Isn't it the same idea of x is defined and y is defined, and they're both in terms of a third variable? So parametric can be time, or it can be theta. I haven't really seen any other variable besides t or theta be used for parametric equations. But the idea is if you see an x equals and a y equals parametric, whatever the variable is. So in your calculator, yes, you would still put 2 cosine of t and 3 sine of t. So we'd still use the t, that's all we got. But you might see it in formulas or in problems with the theta. Pretend it's a t. How would we eliminate?
If theta's t, then
Solve for it. Okay. You gross, we have to solve for theta. How do we solve for theta, guys?
divide by 2 and
Can't do inverse yet. Divide by 2 first. So you say x over 2 is equal to cosine. But then Brandon, you said you have to use what?
inverse.
Inverse to undo the cosine. Oh, gross. So theta equals cosine inverse of x over 2. We're going to take this expression and go plug it in. That we could, and we would get something. But if I ask you guys, what is that? Who would you gonna answer? Now I could do something simple. Just because I know calculus 2. This isn't actually calculus 2, it's just a technique that's used in calculus 2. And I could say, you know what? Hold on. When we had to think about inverse before, we would think, so that means this is an adjacent over a hypotenuse. And I could make the adjacent x, I could make the hypotenuse y. And from that, I could do Pythagorean theorem, from which I could go ahead and figure out the square root of hypotenuse squared minus adjacent squared is opposite squared. And then I could say, hey, who's sine of this guy? And sine of this guy is going to end up being y equals 3 opposite over hypotenuse. I wonder if there's another way. This way works. Maybe a little spiffy. It technically doesn't use any calculus. It's a pre-cal thing that's shown in calculus, but do you want me to show you another way that might be a little easier? This is good. It's actually great. But we can use this thing called sine squared plus cosine squared is 1. But I don't see a cosine squared. So we make one. How do we make cosine squared if he's not already? Square him. Oh, but we can't just randomly square one side of an equation. What are we going to do? Square both of them. So we can say from these equations, here's the other one. Let's see if they match up. We can square the x, and square 2 times 2 is 4. We have a cosine squared. We can do the same thing with y. Ooh, now we have a sine squared. Do you guys remember, in elimination, we have systems of equations, we have like x's and y's and numbers and x's and y's and numbers, and we add them together to get to a better place? We can do that with any equation, including this one. But guys, is anything special going to happen if I do 4 cosine squared plus 9 sine squared? But what if I was to just have cosine squared and just have sine squared?
Equal 1.
And then I was to say, hey, let's do some elimination.
Ooh.
Then I was to say, well, let's just write what we got.
Oh, so bad. Who thought of that? Who else thought of it?
Oh my gosh. And then we say,
First one.
how do we eliminate those guys? Not only are we able to eliminate, but we also get to say,
It's an
okay,
ellipse.
look, it's an ellipse.
You guys know good, aren't you?
Over 2 and over 2 and up 3 and down 3, it's an ellipse centered at 0, 0. With an over of 2 and an up of 3. What? Maybe we should memorize them. But it is a conic section, and conic sections have special equations in other modes. They don't just show up in rectangular.
Not even Ella saw that coming.
Wait!
How does this come?
But aren't these different? Or are they? Isn't this one just solved for y? What would happen if we solved for y? Yeah, multiply everything by what? 36, get a common denominator, I suppose? We would end up with 9x squared plus 4y squared equals 36. We would subtract the 9 squared, divide by 4. We would plus or minus square root both sides. We could pull out a 9, which would square root to be 3, and we could square root the 4 to be 2. So, you can figure out that method, or figure out that method. Both of them work. Both of them get you a right form. But which one's going to be easier to graph by hand if we had to? The ellipse one. These conic sections are coming back. It's all coming back. Yeah. We technically have 2 chapters in our book, but we're skipping chapter 11, just doing chapter 12. The last thing of the section, kiddos, which is good because we're almost done. Oh, hey, I'm just going to say that's an ellipse. We already figured that one out. Okay. The last big idea, those are just homework helps. The last big idea is this page. We have 4 minutes. Let's see if we can get there.
Let's do it.
I must have saved the hardest for last. Finding the parametric equations. What if they give us the path and then they tell us to use certain parameters? Hey, if they're telling us about the parameter, they better tell us something about t, or else we're going to be in trouble. So if we're given something in rectangular or function mode, aka y equals f of x, we don't know anything about time because we just have the path. They better tell us about time. And if they tell us about time, well, how do we make parametric equations? If they tell us about time, how do we get the parametric? We've gone to parametric to function, x of t, y of t to y equals f of x. How do we go backwards? Oh, this sounds hard. Wait a minute. So they tell us y equals 1 minus x squared. And then they tell us use t as x. In parametric, don't we need an x equals and a y equals? This looks hard. Wait, who is x? Oh, that's easy. Wait, who's y? Cool, that was rough. Who is t? Well, they have to tell us about time. Okay, fine. Who is x? X is just t. And then take who x is and plug it in. Oh. How about letter B? Who's x? Oh, it's okay. What are we going to do? For x. So we can do t minus 1. It's probably how most of your brains would work. And then divide everything by a negative. So 1 minus t is x. solve for x, get x alone. So what's y gonna equal?
Minus
Maybe not as bad as our last topic as usual. So take the time, take the parameter clues, solve for x, and then plug in for x. Maybe not a big deal. So what are those homework clues I was going to try and show you? I was just going to say, this is an ellipse. So if we see something like that, we can make an ellipse out of it. The only thing that could be different, guys, is you could have an H. Pause. You could have an H instead. And then we were just gonna use a graph and graph it with your example. That's it. Kiddos, 10, 6, done. Happy spring break. You're almost done.
Thank you.
Persevere. Persevere for today. Thanks, you guys too.
So I said no to
Oh, just. Do you have a couple done or a couple left? Yeah, that's totally good. Thanks. Thanks, you too, Ben. Sam, you're back. You're doing okay?
Let me check my other packet. Look, I only have a 5.
Oh, there's change in the cup. You're missing. You have all the odds. Missing a couple evens. Okay, so I'll check evens later. The odds are good.
You might want us to write in radians.
Oh, no. Degrees is good. Degrees is good. Good question.
Thank you.
Yeah, go ahead and pay the cup.
Are those good?
Yes, they are. You can take them. Thanks. Oh. You can